This is a physics problem that we had last semester, so I thought it was pretty interesting. A train car with some mass, and I'll say the mass is 9,000 kilograms, is going to be coming down this track, just rolling with no friction, so nothing's going to slow it down. And it's rolling at some initial velocity, and it's going to hit this stopping system. Now, this stopping system is a larger spring. I'll draw that larger just so you can see. A larger spring, inside of which is a smaller spring. And the larger spring is much thicker. It's a wider gauge metal, and so it's going to be it's going to have a whole lot higher spring constant. Not a whole lot, but, well, yeah, a whole lot. And so this train car comes down here and it's stopped by these two springs. So the smallest, the inside spring, can compress 20 centimeters before it engages with the larger spring, which can compress 40 centimeters until the gauges of the wire of the spring touch each other, in which case it's compressed entirely and it can't compress anymore. And the problem was, it asked, given this information, and here's the spring constants, so the smaller one, its K1 is 1,800 newtons per meter, and of the larger spring, K2, it is 2,900 newtons per meter. And the question was, find the max VI so that it can still be stopped. Now, the way we do this is we take the energy. So what's the initial energy in this entire system? Well, this isn't moving, but this is. This doesn't have any initial energy because it's not compressed. It's at its equilibrium position. This is the only thing with the energy, this moving train car. And so the initial energy, the total initial energy of the entire system is the kinetic energy of that train car initially, which is 1/2 mv squared, mvi initial squared. Now, it's going to go and compress the spring, and all its kinetic energy is going to be taken away and transformed into the potential energy of this spring. So, when that happens, it will have no kinetic energy at all. It won't be moving. And so we know that it stops it by the exact same amount that it had. Essentially, it cancels it. So the energy of the two springs, E springs, will also have to be 1/2 mvi squared. These two are equal because they cancel each other. They're equivalent. And so the way to solve this, let's first look at the hardest thing here, I guess, is just setting this up. But let's look at the energy of a spring. So the energy of a spring, over just one single spring, is 1/2 kx squared, where x, and this is going to be negative actually, but since it's in the negative direction, it'll be positive. And so when we add, and what I mean by that is when we sum the two, negative and positive, they'll equal 0. So if you move one of them over, then it's positive still. It becomes positive. And so 1/2 kx squared is the energy of a spring. Now, the energy of these two springs, let's look at what's going to happen. The first one is going to compress. So I'll see the total energy of these springs, make sure you guys can still see that, awesome, is going to be equal to 1/2. Now let's consider, this is K1, let's consider the entire, everything that's happening to the K1 spring. So you may want to say it's compressing 20 meters, or 20 centimeters, and then it compresses together with the second spring. So you may write something, when you first try this, that looks sort of like this, because you're 20 centimeters, and then you say, well, it's compressing together with this other spring, and so that'll be K1 0.40 meters squared plus K2, and that's also going 40 meters squared. But this is incorrect, and I hope you can see why. And the reason is because we have already said that spring 1 goes 20. So if we then say 20 centimeters, so if we then say it goes 40, the fact that we say 40, x here, is measured, is the displacement measurement from equilibrium. So it's not actually going 40, it's going 40 more than 20. So this would be incorrect, because this preassumes that it's starting from equilibrium, which it doesn't. It starts from 20 after that point. And so I hope you can see why that is. And the actual correct way of setting this up would be to say that let's list the entire change in energy, or the entire energy that's going to be stored in spring 1, the way it's going to change, its energy, and that is 20 plus 40, so that's actually going to be 0.60 centimeters squared is the entire displacement from equilibrium for itself, so 20 and then 40 over. And then also the change, the energy of K2 and its total displacement from equilibrium, which is going to be, as we would expect and easily see, 40 centimeters, which is 0.60 meters and 0.40 meters. Now, because this is equal to 1/2 mvi squared, let's notice that each of these terms has a half. And because that is a constant multiplier, taking that away or putting it on doesn't change the statement that they're equivalent. It doesn't change the nature of the equivalence. And so we can just go ahead and get rid of those to simplify it. Or similarly, I could say divide 1/2 by this side and this side. They all go away. That's how most people are taught it. But theoretically, the equivalence is the same, and that's why. Now, doing this, we can see that we just have I won't bother writing that. We just have mvi squared equals k1, the displacement squared, and k2, the displacement squared. We're summing these total changes in energy of this spring, the total potential energy. Now, if I want to find vi squared, which is what we're solving for, is vi, I can just go ahead and divide each side by the mass of the train car. And I won't plug in the numbers because I assume you can do that yourself, just to save time and space. And this is going to be K1, I'll just plug in these because I already have, 60 centimeters squared, plus K2 times 40 centimeters squared. And that's all over m. Now if we want to find just vi, not vi squared, of course we would take the square root of this. So K1 60 squared plus K2 times 40 centimeters squared. And of course I'm writing this in meters. And all of that over m, and this will be our answer. This is the maximum, so I'll say Vmax, Vi max, and that is going to be an initial velocity of the square root of K1, its displacement is total displacement, 0.60 meters squared, plus K2 times its total displacement squared, 0.40 meters squared, all over 2, or all over m rather, which is under the radical entirely. So I hope this helps you if you're working on something yourself that may be practically similar or theoretically similar, to kind of learn how to deal with energies. And so when dealing with energies, the main takeaway here is not necessarily the sequence in which something is happening, but the total change in energy of each component or element of the system. So like we said before, not necessarily the sequence in which this changed from 20 and then 40, but rather the entire change of this element of the system, which was the longer, skinnier spring. And so I hope this helped, and I hope you enjoyed it. And thanks for watching, and I'll see you next time.